Okay, welcome to Lab 11, which is the Miller effect lab. So what we're going to be doing today is actually verifying Miller effect in a common emitter amplifier. So what we have is an amplifier here. Now the problem with doing Miller effect with the built-in CMU is that our frequency would be in the tens of megahertz, and I don't know if our equipment can make reliable measurements. So what we're going to do is we're going to install an exaggerated amount of capacitor for CMU. We're going to have a CMU of 47 picofarads instead of the 4 or 5 picofarads that it usually has. And then we're going to install this here, see what kind of a frequency range that gives us. Then we're going to take it out, do a Miller conversion on it, multiply the gain by 47, and hang that capacitor here as this blue CM, and see what kind of effect that has on our frequency. And we're going to also hang it over there and see if the overall frequency response with those two is the same as it is with CMU in place. So we're going to run one test with CMU in place here. Then we're going to unplug it, plug in CM there and this capacitor over here, and test it again and see if the results are even. And then if they are, then we're going to have definite proof that the Miller effect is valid for measuring high frequency response. So we're going to start with the circuit by doing a DC analysis. So VBB, IB, IC, G sub M, R pi. We don't really have a value for little RO, and I think we can leave it out. It's going to be about 100K next to a 3K. It's kind of inconsequential. So we can leave that out. And then from that, we're going to calculate voltage gain, and we're going to need that to do the Miller conversion. So we're starting with the CMU of 47 picofarads. We're going to multiply that by our AV value. And then we're going to plug that, get a capacitor, that value, plug it in here. And then plug this capacitor in over there and do the frequency response. So I'm going to leave it to you to do these calculations. You've done them before. And from now on, we're just going to build the circuit and conduct the tests on it. So everything from here on is going to be at the bench. Okay. So here we are at the bench. For equipment, we have a Keysight 33500B waveform generator, number 793. We have an Agilent EE310 dual DC power supply, number 688. And we have a Tektronix MSO 2012 mixed signal oscilloscope, number 635. And a generic breadboard, number 5. So we're going to start by building our circuit. I left all the parts over there. Oops. Okay, thanks. Okay, we're also going to be using our calculation of beta of about 250. That seems to be about what people measured from doing lab 7. So I used a beta of 250 for all of my calculations. So let's start with our transistor. We're going to plug it in over there in 3 consecutive holes. Emitter, we have a 1K resistor going to ground. 1K. Brown, black, red. That one looks like it. Emitter resistor, 1K going to ground. And we have our bypass capacitor, CE, with the stripe going toward ground, also from emitter to ground. Okay. And then on the base, we have a 51K resistor that is green, brown, orange, from going from base to ground. Base to ground. Get in there, okay. And then we have our 3K resistor, which is going to be orange, black, red. That looks like 30K. We may have to go get a 3K resistor. Orange, black, red. Okay. We'll come back to that. We have a 150K resistor, brown, green, yellow, going from base high. Base to high. And then we have a 3K resistor, and we have a lead-in capacitor, a C1. I just went ahead and got 10 microfarad capacitors for C1 and C2. C1 goes to the base. From there, and then from there we have a RS as a 1K resistor, brown, black, red. Coming to VS. All right, oh, thank you, sir. Here is a 3K resistor going from collector to VCC. Collector to VCC. Okay. And we then need to have our C2, our output capacitor, going from collector to load resistor. Load resistor is a 10K, a brown, black, orange, going to ground, brown, black, orange. Going to ground. And I believe that's everything. So we can now connect up our signal generator. Let's turn on the instruments and let them warm up. We have our signal generator going to RS over here, and we can just plug in the ground back there on the power supply. And then we have got our power supply itself. We need a red jumper, and we can dial up 15 volts here. I think I've scared everybody away. They all left. 15 volts going to the plus of the power supply. And we have our ground going to ground. This should bring our circuit to life. Yeah, we got 2 milliamps of current. That's good. And finally, our scope. We have channel 1 is going to go on V in, which is on the right side of the base resistor of RS. And channel 2 is going to go on V out, which is across our RL. And let's connect up the ground for the probes over to there. Okay. So it looks like we have a signal. Let's turn on the output channel, output on, and we have some kind of a signal there. Rather big. Okay, let's turn on channel 1. And it looks like we are overdriving it. We are expected to get a pretty large gain out of this amplifier. You can see down here where they're driving the transistor into saturation and how that's affecting the signal generator. So let us reduce our amplitude, parameter, amplitude. Right about there, we have a nice, relatively undistorted output. And we'll have a very fuzzy input. And let us clean that up. We're going to put on the triggering, on the averaging. And let's see what kind of a gain we've got. Okay. So right now we have an input, and let's see what frequency we're at. We're at 1 kilohertz. So we're still getting a little bit of distortion on the input, but the input that we have is 2 divisions, 100 millivolts, and the output is about 9 volts. So we have a gain of about 90 right now. Okay. So I'd also like to make sure that our DC Q point is correct. So the way we're going to do that is we're going to shut off the output. I'm just going to unplug it. And let's look at the voltage on the collector. According to the DC Q point, the collector should be sitting at about 7 volts. So let's take a look at it with the scope over here and put channel 2 on DC coupling, which it is. And it's on 2 volts per division. So that's 2, 4, 6. We're just at above 7, about 7.3 volts. Which means that our beta is fairly accurate. We had assumed a beta of 250. This is slightly higher, so I'd say our beta is going to be slightly less, but it should be still pretty close to the ballpark. Okay, so we can go ahead and reconnect our signal generator. and go back to channel 2, AC coupling. Menu off. Okay, I noticed just a little tiny bit of clipping down there, so let's reduce our amplitude by just the smallest amount. There we go. Okay, so, and I'd like to set up a measurement on channel 2. So let's do the measurement. Okay, measure. Add measurement. Channel 2. We're setting this up for peak to peak. Okay, add measurement. Okay, so right now we've got 8.12 volts, and the reason we're making a record of that is because we have to multiply that by 0.707. So let's set that to a nice round number like 8. So 56, 55. Okay, so right now we're measuring 7.99 volts. We're going to call that 8 volts. So now what we're going to do is with our 3 dB frequency is going to be 0.707 times that. So 8 times 0.707 is about 5.66. We're going to sweep the frequency up until we get 5.66 volts right here on this reading. So our amplifier seems to be working. I'm going to go ahead and install our 47 picofarad capacitor here between base and collector. And these are not very friendly marked. It's too small to put a lot of markings, but it does have the number 47 on it. So we're going to install that between the base and collector of our transistor. And hopefully we're going to still get that back to about 8 volts, which it looks like we are. Now it's a little bit disturbing that we have some phase shift there, but it's not much. We're just going to have to live with that. So now what we'll do is we're going to sweep our frequency up until the blue wave drops to 5.66. We're going to sweep the frequency up, and that'll tell us the pole due to C mu. So frequency, we're jumping kilohertz now. There's 2 kilohertz. We're still at 8. If anything, we're a little higher. We're up to 9 volts. Wow, okay. So let us adjust our amplitude again. Let's bring it down a little bit to get rid of the clipping. Remember, we want to go to the peak value. Okay. We'd still like to get back to about 8 volts. Okay, there's 8 volts there. So now let's continue to sweep the frequency up. We have a new midband gained over here, and notice we have a little bit less phase shift, so that's a good sign. So we're going to continue to sweep our frequency up. 2 kilohertz. 3 kilohertz. We're still at 8, a little bit above that. Okay, we seem to have maxed out at this frequency about here. So what I'm going to do is bring it back down to 8 volts again. And the reason this is happening is because we're not quite fully bypassed. We're not quite in mid-band condition. So let's get back to 8 volts. Okay, now let's go back to frequency. And what we should eventually see is our frequency is going to start to, our amplitude is going to start to come down. So there we are at 12 kilohertz. We're still at around 8 volts. There's 14 kilohertz around 7.4, 16 kilohertz around 7.2. So we're getting close to the pole frequency. Let's adjust the wave. Remember looking for 5.66. Getting closer at 26 kilohertz. .29 kilohertz. Okay, we're right about there at 28 kilohertz. So at 28 kilohertz, we have found now our pole due to our artificially inflated C mu. Okay. All right, so the next step is let's go back to midband. Let's bring it down to 5 kilohertz and take out C mu and replace it with Cm. So C mu is 47 picofarads. Now what we can do, we have a choice now. Do you want to multiply by the calculated gain or by the measured gain? So let's bring this back down again. And the question is kind of a philosophical one. Is do you trust more the measured gain or the calculated gain for the Miller conversion? And for me, I would trust more the measured gain. So the measured gain is going to be 8.17 volts divided by, let's put a measurement for channel 1 also. Measurement, add measurement, source, channel 1, peak to peak, okay, add measurement. So now we have 8.16 divided by about 61 millivolts. Just do a quick calculation of our measured gain. So calculator, 8.17 divided by 0.061, 134. We have a measured gain of about 134. So let's do a quick calculation. 134 times 47 picofarads. I'll do it on here. 134 times 0.047 nanofarads, 6.3 nanofarad. So we would want to get a Cm of 6.3 nanofarads, or 0.0063. So at this point, we would go to the parts room and get a capacitor of that value and place it between base and ground. All right, so now we have a capacitor 0.0068. We picked up some nasty oscillations on channel 1, even with the averaging on. I'm not sure why that is. But let's hang a capacitor on and see if that makes a difference. So again, we're installing this capacitor from base, there, to ground, there. Okay. And we have an output of 7.73. It was at around 8 before. Let's see if we can bring it back to 8. We'd like to keep it to 8. Okay. So now we can bring the frequency up again. We're at 5 kilohertz now, and we want to keep this going up until we get to 5.66. So here we are at 8 kilohertz. We're still at 8 volts. 9 kilohertz, 10 kilohertz. 15 kilohertz, we're down a little bit. 16, 17, 18. Let's spread it out a little bit. And again, we're shooting for about 5.66. 24, 25, 26, 27. This is where we were last time. And we're off by a little bit. We're at 6.3 volts. Let's keep going a little higher. .66, but we're at 36 kilohertz now. So the error could be that this capacitor is off. These capacitors are typically 10%. If this 47 picofarad, actually these ceramic capacitors are more like 20%. So if this is off by 20% and we're going to magnify that error by a factor of 130, we could have a significant difference with this capacitor here. But this is our 3 dB frequency now. It is at 36 kilohertz compared to 28 kilohertz. And that's what we're getting. So we could try going with the calculated value of that capacitor. Let's bring the frequency down back to 5 kilohertz. If we use the calculated value of that of Cm, what we would get is a 0.082. Let's just plug that one in and see if it does any better. So the calculated value goes from, again, from base to ground. Okay. And we seem to have lost our signal. What if it's touching something it shouldn't be? Yep, okay. All right, so now we're at 5 kilohertz at 8, and let's sweep the frequency up again and look for 5.6. Right there. Which at 31 kilohertz. So it seems that our calculated value of Cm was closer to the target than our measured value from gain. So the Cm that we got from the calculated gain was closer than the Cm that we got from the measured gain. So 28 kilohertz versus 31 kilohertz. That's pretty close considering these capacitors, especially the 47 picofarad, is a 20% tolerance. These other capacitors, I know this type here is typically a 10%, and those are a little bit more precise. One thing I might have done is to measure that capacitor before I plugged it in, and maybe we can do that after the fact to come up with its actual value. Do we have a capacitance meter in here? We do.
I don't know how well it's going to get to that.
Yeah, because the leads themselves have capacitance.
We can get it now.
Oh, okay.
You can give that a roll.
Let's see how this works. So let's measure the capacitance of our 47 picofarad capacitor. However, this won't be terribly accurate because there's capacitance in these leads. So it's better to have the kind where you can just plug the capacitor directly into the meter. But let's pull this capacitor out and measure it. And even my hands would affect the reading. Just the body capacitance would affect the reading also. So let's see if we can get that to hold still. Not easily. This is reading 135 picofarads, which can't be right. The leads themselves are 88 picofarads. So 135 minus 88 is 47 picofarads. Wow. According to this meter, this capacitor is spot on. Not bad. But there's a lesson. The leads themselves are 86 picofarads. And then with the capacitor in place, it's 135. 86 to 135 is 14, and 35 is 49 picofarads, which is impressively close for a low dollar part. So I think that the value of our capacitor was pretty good. It's pretty close to what's marked. So sources of error could be in measurement of gain because our input signal was noisy. It also could be because our beta value is off and because our calculated gain has all kinds of room for error because the input signal is small and weak. But that's a demonstration of Miller effect, and hopefully it's convinced you that replacing C mu with a Cm and a CO prime gives you the same pole frequency as we've been doing with analysis. This may be our last lab. We may be doing one more lab next week on power amplifiers. We'll have to see how the progress is. A lot of the class is very far behind in labs. So, but that's it.